6.6 is on moments and center of mass, and we'll define what that is. So, if you've done physics, then you've seen this sort of thing before, talking about center of mass and how to calculate it. But we'll go through how to set it up. So, consider a point mass system. So, you have all this. This is a rectangle. It's actually, of course, has to be more like 3 dimensions to have mass, but think of it as all the mass is centered in one spot. So like right there, and this one be like right there. So these are considered point mass systems. So what we are interested in really is basically the balance point. Change my font color. So balance point of the system. So you can picture that this is like a teeter-totter and a balance point. And over here, of course, it would fall to the left. And way over here, it would probably still fall to the right. So the balance point of this, who knows what it really is, but it might be something like right there. That's the balance point. That's considered what we say is the center of mass. And we denote it using notation x bar, like that. So x bar is the center of mass of that system. And you picturing this is like an x-axis. So wherever they're at, it doesn't really matter what the origin is. It's just some distance away, so some coordinate. Okay, and so that would be that value of x, or along any linear, any line like that is considered a balance point. So let's look at then the distance from each of these masses, mass 1 and mass 2, to this point. So we can look at this distance we'll call d1, and then this distance right here we call d2. Oops. So d2 is the distance from the center of mass, whatever that is. We assume it exists, right? So there is a point that would balance that. And then we have that mass 1 times this distance d1 must equal the mass 2 times the d2. So that implies a balanced system, that the distance times the mass is equal to the distance times the mass. So let's suppose, as I was describing, x bar is the center of mass of M1 and M2. So it is the center of mass of M1 and M2. So then what we do is we can basically solve for x bar. So let's do this on a system, another diagram here, and then I'll show you how to solve for it. And we're basically just doing a warm-up for what we'll do in calculus. This is a kind of review of a point mass system you might have seen in physics. And then eventually our goal is to use integration, of course, to figure out these sums. This is just two masses. We're going to do like a continuous mass shape sort of thing. So we have that x bar is here and that it exists, basically. And then let's say that this value is your M1. Let me fix that. This value is M1, and then the position would be X1. And then say this value here is M2 and X2, whatever position on the system. So the distance is for this is x bar minus x1, and this distance would be x2 minus x bar. So we can solve for x bar by setting up that equality. So m1 times the distance, which is x bar minus x1, is equal to m2 times that distance, which is x2 minus x bar. And there we can solve for x bar and figure out a way to find the center of mass. So we distribute m1 x bar minus m1 x1 equal to m2 x2 minus m2 x bar. Bring over x bar on one side. We have m1 x bar minus m1 x1. Oops, I was rewriting the same thing. Let's try that again. So let's see. So m1 x bar plus m2 x bar equal to m1 x1 plus m2 x2. Factor and divide, and x bar is equal to basically the sum of m1 x1, m2 x2 over the sum of the masses. So you basically will end up dividing by sum of the masses on each of these cases like that. So that would allow, so if we knew the position of each of the masses and we knew the mass of each, then you just add them up and then divide by the mass. So this sum here and here is what we call the moment. Okay, and I'll define that. So what we're interested in, and I'm going to do another case here in a second, but what we're interested in is really actually more like this, more like we have some sort of plane thing. Let me redraw that. So we're interested in something like this. So you have some sort of figure that has a thickness to it, and we're just going to assume it's like basically like that. So this is some region in the xy plane, and the thickness we'll just consider being like what it's the thickness is uniform, so that it's not going to change. So we're looking at like what's the balance point of that. The balance point of this one, who knows where it would be. Maybe right here. Okay, so if you were to balance that, that's what it would look like something like that. So we're going to balance it at that point. That's the center mass of the whole thing. Okay, so this is what we call, or they call in the book, a lamina. Okay, so this lamina is basically a uniform, or the same thickness, doesn't change. So basically it only changes, the density only changes as you move across the system, not through it, if that makes sense. So a little recap about stuff too about density. So density is equal to mass divided by volume, which we all know that. And we'll use a notation like a cursive M for mass, like the total mass kind of thing, and then volume. So mass, you can solve for that, and it's basically the density times the volume. Now this lamina thing, does it have volume? Well, kind of. I mean, it has to have volume, but we basically are only considering the area of it in this class. It makes it kind of like we want to simplify it a little bit. If you go on to Calc 3, you look at the same process with volume, but we're going to call it basically area density instead. It's kind of weird, but we need to do it to get us going. So what we're going to consider for mass, oops, I didn't mean to do the cursive that time. So our mass is going to be what we call area density. And then times area. So it's basically saying that the thickness doesn't matter, and we'll multiply by a constant to give us that. So the book, I think, uses a delta. I don't like using delta because it confuses us with the epsilon delta stuff. So I think the other books I've used is rho. It's kind of like that. So rho is the constant we will use for area density. So rho is equal to mass divided by volume, or we'll say mass divided by area, and it's like area. It's a lamina. So it has volume, but all we care about is the area of it. So we'll consider mass is going to basically be rho times A. So this constant rho is area density in this section. So it's like having a thickness of 1 that doesn't really change anything. And then as you go through it, kind of up and down through the lamina, that won't change. So it may change from over here to here, but this direction vertically through it, not going to change. All right, so just you got to just stick with it. I always thought it was kind of weird, but we need it to get to the next step, next level. Okay, next, let's look at a coordinate system with a bunch of point masses. So let's take a look. Oops. Take a look at this. So you have, we were just looking at the XY, or just one axis. Now we want to look at 2 axes. So just roughly speaking here, we're going to put a bunch of point masses over here like this. And we want to find the center of mass of it. So where is it? Is it here? Is that the center of mass of the whole thing? So that's what we're going to do. So let's suppose you had, let's change the colors just for fun. Suppose you have these point masses. We'll call that M1. I'm just randomly putting them in here. M2. M3. Let's put one down here. Put one in each quadrant. What am I on? 4? M4. Okay, is 4 enough? 4 is enough. Do 4 of them. And so each of those masses have a corresponding ordered pair that's associated with them. So the ordered pair, this would be x1, and then this would be your y1. This would be your x2 and your y2. Okay, so let's label all those. That's your 3 and your y3. And this would be x4 and your y4. It's the same. So this is the 2-dimensional case, closer to what we'll be doing for our calculus stuff. So then we want to talk about what we call the moment. So the moment of the system. So we called it, when you have a bunch of masses like that, and we use this terminology a lot, but it's called a system. So moment of the system S about, and then we'll do the, you say moment about the axis. So moment about the y-axis, we say my is equal to the sum of what that basically that product was back here. So we're basically saying we're going around this y-axis. So the moment is this same calculation, essentially. It's the top of that is the moment about the y. It's the distance times the mass. Distance times the mass. And it's can be negative, right? Because if you're around the origin. So we're finding a coordinate that is the center of mass. So moment about the y is the sum of all m sub k x sub k as k goes from 1. In this case, it go to 4, but I'll do this more in general, to n. Okay, and then similarly, I'll just put x-axis here as well. Moment about the x-axis is m sub x, and it's the same type of calculation going around, so here to here, here to here, here to here. It's going around the x-axis. So we're looking at the y values. And the good thing is it can be very confusing because of the y here and x here, but I always, you don't have to memorize it because it can be confusing. Of course, in this format of the class, it doesn't matter. Anyway, so moment about the x is the sum as k goes from 1 to n of, and then you multiply by the masses, m sub k, and then now this is y sub k. And then the mass is just the sum of the masses, right? So m, and I'll use like a cursive m, lowercase squiggly cursive m is what I often use because the books do that sometimes, is the sum of all the masses. You just add them up. So it'd be m sub k. So the center of mass ends up being, let's just put that over here, tidy things up a little bit. Okay, so we have moment, this is called the moment about the y, moment about the x, and the mass of the system. So we're going to do the same thing we did back here. We're going to add up the moment and then divide by the mass. And that's the center of mass of each coordinate x, y. So we say, so the center of mass is x bar is equal to moment about the y divided by the mass. And then moment, or the y coordinate is moment about x divided by the mass. Okay, so that's how you do the calculation. And guess what's going to happen? What's going to happen to those when we end up doing the calculus? Those end up being integrals, and we'll derive that soon. But what I was about to, if I derive that right straight away, then it doesn't make any sense, really. So we want to do this case first, and then derive the case that has functions and stuff. All right, so let's do an example using this technique here, and going to be given a bunch of masses and then a bunch of points, and we'll find the center of mass. So given the point masses, four, 8, 3, and 2, and we'll just do this in kilograms. And we'll just say that are located at, and we'll just do like respectively, located at, and then this is the position of them. So it's -2, 3, 2, -6, 7, -3, and 5, 1, respectively. Which means essentially in the same order that was given. So that's corresponding to those, like that. So what you do is you find moment about the y, moment about the x, center of mass, and then you divide them like that. All right, so find moment about y, moment about x, and the total mass of the system, which would just be adding those up, right? And those will be the same, right? You see that the denominator of those will always be the same because it's the sum of the masses, just 4 plus 8 plus 3 plus 2. So let's calculate, and then from there we'll be able to calculate x bar, y bar, which is the center of mass. Okay, so that implies we can do that calculation. So moment about the y, I did that first, I'll do it first here. You do the product of 4, and then it's times the x value, and then 8 times the x value, right? So that's what you're doing. So it's 4 times negative 2 plus 8 times 2 plus 3 times 7 plus 2 times 5, and then you add that up. Let me double check. Okay, looks good, and that ends up being 39. You can check that. Moment about x, go ahead and try this on your own. 4 times 3, 8 times negative 6, right? The masses are the same. 3 times negative 3, 2 times 1. You add that up and you get negative 43. And then you just add the masses up. So the mass is the sum of those. Just to see if you can finish this. So it's 4 plus 8 plus 3 plus 2. That adds up to 17. So x bar is going to be moment about y over the mass, which is 39/17. Y bar is moment about x over the mass, which is negative 43/17. And so the coordinate center of mass is just that. 39/17 and negative 43/17. Don't change that to a decimal, please. You'll freak me out. Okay, leave it as a fraction. Okay, so that's the idea of the non-calculus stuff, but the technique will be very similar of how we look at it, how we interpret the lamina that'll essentially be a area between curves. We just did area, right? Or earlier we did area. So we'll look at area with a changing area. So the mass, like what's going to be the center of mass of that? And the density will be constant. So constant density rho, area mass density. But the shape is different. The shape is determined by the function values. So this will be like f and g. And then you do the same sort of process, which I will derive in the next video.